We now discuss the concepts of angular velocity and angular acceleration. Just as our physical intuition of how fast something is moving is connected to linear velocity, the idea of how fast something is spinning is related to angular velocity. And just as linear velocity is connected to linear displacement, angular velocity is connected to angular displacement. The average angular velocity is defined as the angular displacement divided by the elapsed time. Or, we write, the average angular velocity, omega bar, equals theta minus theta 0 divided by t minus t0, which equals delta theta divided by delta t. There are two things to note about this equation. First, the units of angular velocity are radians per second. Second, the sign of the angular velocity is determined by the sign of the angular displacement, delta theta. Therefore, just like the angular displacement, the angular velocity is positive if it is counterclockwise and negative if it is clockwise. The instantaneous angular velocity, omega, is obtained by reducing the time interval to an infinitesimally small value, or omega equals the limit as delta t approaches 0 of delta theta divided by delta t. From this point forward, reference made to angular velocity will implicitly mean the instantaneous angular velocity. When the average angular velocity is meant, it will be explicitly indicated. Just as we have a physical intuition of linear acceleration, for example, a car accelerating from a stoplight, we have an intuition of angular acceleration. Think of a helicopter blade starting from rest and spinning up to full speed. The average angular acceleration equals the change in angular velocity divided by the elapsed time. Or alpha bar equals omega minus omega 0 divided by t minus t0, which equals delta omega divided by delta t. Note that the units are in radians per second squared, and that the sign is determined by the sign of the change in angular velocity. The instantaneous acceleration is obtained by decreasing the elapsed time to an infinitesimal value, or alpha equals the limit as delta t approaches 0 of delta omega divided by delta t. Most often, we will deal with problems involving constant acceleration, where the average and instantaneous accelerations are equal. As in the case of linear motion with constant acceleration, rotational motion with constant angular acceleration will lead to kinematic equations for rotational motion. In summary, the average angular velocity is given by omega bar equals delta theta divided by delta t. The instantaneous angular velocity is omega equals the limit as delta t approaches 0 of delta theta divided by delta t. Angular velocity is measured in units of radians per second, and the direction is determined by the sign of the angular displacement, delta theta. The average angular acceleration is given by alpha bar equals delta omega divided by delta t, and the instantaneous acceleration is given by alpha equals the limit as delta t approaches 0 of delta omega divided by delta t. Angular acceleration is measured in units of radians per second squared, and the direction is determined by the sign of the change in the angular velocity, delta omega. Kinematic equations, analogous to those for linear motion with constant acceleration, can be formulated for the case of angular motion with constant angular acceleration.